This is Geography 2104, Lesson 11, Spatial Analysis in Geoprocessing. I am Professor Hurley. In this lesson, we'll be looking at various spatial analysis and geoprocessing techniques. These techniques are usually how we start to apply GIS to a problem and find a solution. Spatial analysis is the process by which we turn raw geographic data into useful information. It includes all the manipulations and methods that can be applied to geographic data to add value, support decisions, and reveal patterns and anomalies not immediately obvious. This is an important definition, so it would do well to know it. Effective spatial analysis requires an intelligent user, not just a powerful computer. You need to know why and how to push what buttons. Spatial analysis helps us in situations where our eyes might otherwise deceive us. What kind of questions can GIS answer for us? Up to now, we've been pretty much making maps with different layer combinations, exporting select data sets, and reworking those into new maps. But let's do an overview of the analytical capabilities of GIS. Firstly, location. Where is something in relation to something else? The notion of calculating quantity. Distance, area, height, etc. in simple counts. How many of a certain feature lies within another? Hospitals in Fairfax County, for example. How many pediatricians in a certain zip code? Patterns. It is hard to discern distributions, relationships, and trends from written or tabular data. To look at distribution patterns, they can be discrete phenomena, such as specific patient addresses, a specific disease like West Nile or swine flu cases, or social phenomena amalgamated to enumeration units, something like median income or poverty per zip code, or percent of kids fully immunized for a particular county. You can visualize and correlate the location of one factor with another, such as how epidemiologists correlate the location of disease outbreaks to environmental hazards or points of pollution. Trends, or temporal aspects. Maps give you the ability to compare past to present trends, such as how patterns like those mentioned above, change over time. Conditions and relationships. These are all the other spatial elements that surround and affect the feature that you are interested in. Like for West Nile cases, we might be interested in population density in the area. You might want to map hydrology, swamps, marshes, or habitats. You have the ability to integrate data from a host of diverse sources, utilities, transportation networks, cadastral data, survey data, patient databases, survey participants, and all of these could be in different digital formats. Implications, or planning for the future. It could be visual aids for predicting the future. Like a map of West Nile virus, you can look at where it could spread to if a bird contracted the disease and carried it on its migratory path. You'd map populations underneath to see how many people could be put at risk. The next few slides show maps of how other people have used spatial analysis for their specific needs. The map on the left is a simple isopleth map here showing the spread of bubonic plague across Europe. This map is both historical and epidemiological at the same time. Our second map shows the approximate migratory patterns of birds, which in the light of the bird flu scare was crucial information in identifying potentially affected countries and heavily populated metropolitan areas. Finally, the map shows the spread of white nose syndrome in bats, an endangered species. A map on the left used data gathered at the point level, in this case crime data, and from these points a raster hotspot map was created to indicate areas with high crime rates. Our second map looked at security and proximity. The second map shows the registered home address of sexual offenders and their proximity to schools. This is obviously a very sobering but necessary function of GIS. A map on the left, these maps here are showing fire incidents and locations of stations. Here again we have our map of damaged and destroyed buildings within Port-au-Prince, and same idea, heavier areas here and lighter regions here. We could also use GIS for plume modeling so that affected populations and infrastructure can be identified or calculated. On our right, we have modeling and simulating again the area potentially affected by a hurricane, in this case Hurricane Rita, based on a trajectory provided by NOAA. Even if this information is available only for a few hours ahead of what's happening, it can at least help us identify settlements in various damage ranges so that the evacuations can be implemented. This map is what some believe may be the first instance of geographic information systems, or at least using maps for spatial analysis and not just topographic descriptions of land and features. It shows the 1854 Broad Street cholera outbreak and was the map that supported Dr. John Snow's discovery that cholera is spread by contaminated water. Snow was a skeptic of the then dominant miasma theory that stated that diseases such as cholera or the Black Death were caused by pollution or a noxious form of bad air. The germ theory was not widely accepted at the time, so Snow was unaware of the mechanism by which the disease was transmitted, but evidence led him to believe that it was not due to breathing foul air. The map was drawn after the discovery and used to support his argument. Snow mapped the deaths from cholera in the Soho area of London, the pattern of which clusters around the Broad Street pump. Essentially, he could have used GIS to help him narrow his search focus for the source of the contamination. So, Snow worked with a local passer to have the pump handle removed, after which the epidemic subsided. This is a map, now an old map, of Brooklyn's million-dollar blocks. City blocks that were costing the taxpayer over $1 million a year to keep its residents that would normally abide here incarcerated for various reasons. This begs the question, what else should we look at here, and what early interventions might be possible and less costly? Better education, or community and social services, creating opportunities for you. Here we have principles of spatial analysis. What you'll be seeing coming up are basic principles, measurements, scopes, query, proximity functions, and geoprocessing. Additionally, we have advanced principles, spatial estimation, and spatial interpolation. I want to pause for a second and tell everybody I have spliced in how-to videos from ArcGIS for a number of these up here. So bear with me while I jump around between videos. So we want to introduce a few most common and most used of the many data analysis techniques. First we have measurement, simple numeric values that describe aspects of or simple properties of geographic data, such as length, area, shape, or relationships between pairs of objects, like distance or direction. We use different calculation methods based on data format we're using. We have a vector with distance and Euclidean distance, drawing a straight line between 2 points, constructing a right-angled triangle using Pythagorean theorem to calculate the length of the line. With rasters, we have the same concept, Euclidean distance drawing a straight line between 2 points. And we have Manhattan distance, the distance along the raster cell sides, or, as they say, blocks of Manhattan. You can't pass diagonally through the block, you have to go around it. And finally, there's something called proximity. Concentric zones are calculated from the starting point, so that incremental distances from point A to point B are calculated en route. In vector GIS, length, perimeter, and area data can be stored in an attribute table. Therefore, they only need to be calculated once and then are permanently saved. Scope. Spatial data operations may be classified by their scope. This refers to the geographic extent or area of the input data used to determine the values of the output locations. We act on the data at a given location, and its results are attributed to a feature at another location. This may be the same extent or not. For characterizations, we have local, using data from one input location to determine a value for that same location as your output. Population information for the state of Utah, land area for Utah to determine density, for example. Neighborhood, using data from both the input location and neighborhood or adjoining locations to determine value for the output location. Basically, you're interested in the stuff around a location as well as the location itself. This can be a simple count, or sometimes surrounding locations may carry a weighting factor. Global, using data from the entire input layer to determine values for each output location. Queries. This will look familiar from our database lecture. Queries we looked at in relation to database management, but as they are also important to spatial analysis, we'll reiterate a few things. Queries are the primary method of data retrieval, and they allow us to create new information, but they do not change the older existing database. There are two primary types of queries that we work with: aspatial or non-spatial queries based on structured query language, or SQL, that allow us to query tables like our attribute table, road equals boulevard, and spatial queries. That allows us to query geography or geometry of our spatial data layers, roads that overlap a certain zone. You did this with your Kasungu homework. Aspatial or tabular queries are performed on the attribute table. Users build a set of conditions. If the conditions match, then the matching records are returned. There are two principal ways that we build aspatial queries. Set algebra, using operations greater than, less than, or equal, or not equal to. These can be applied alone or in combination, depending on your criteria. These operators can be applied to numeric, ordinal, or textual data. We also have Boolean queries. These queries use the conditions and, or, and not to select features, and are most often used in combination with set algebra to create compound spatial conditions. Number 3 in the example is a compound expression we have here for choosing an appropriate area to retire: high rainfall for gardening, low taxes, low housing, and low crime. When talking about spatial queries, there are two spatial operations which are the most commonly used. The first is adjacency, used to identify features that touch other features, features that share a boundary or edge. It also can use the concept of distance to a feature or its center point. Also, we have the notion of containment, selecting all features that surround or contain another set of features, or target feature. In the example, we have the Mississippi River. We select all states that contain some portion of that river. And here within the tool itself, we have all the options that can be used within the query. This is spatial and non-spatial queries. So I went ahead and mocked up some data. We've got a shapefile of grassland and a mock-up shapefile of a chemical spill area, and some mocked up sample points. These are the blue points throughout the data here. So for non-spatial queries, we're going to always want to check out the attribute table, because in essence, with the non-spatial queries, we're asking the computer a question about the attribute table. So for the all points, which are these blue points here, we have chemical concentrations in parts per million, and we've got a column for costs in thousands of dollars. And with a non-spatial query, we're going to head and ask something about it that will be highlighted within the records here and additionally on the map. Now, there are two different avenues to do a non-spatial query. There is within the attribute table. You have a select by attributes function. I just want to point that out. And you have at the top of your computer a selection button with select by attributes. They both do the same thing. So with select by attributes, from the top of the screen, we have what layer we want to work with, which would be all points again, which are these blue points here. And we want to go ahead and ask it, type that in again. Chemical concentrations, let's say, greater than 0.08. Now, two things are going to happen when I hit apply here. Number one, on the map, you'll see the points that satisfy this condition, parts per million greater than 0.08. And additionally, you will see within the attribute table, this 0 will change to the number that satisfies the point. So it'll be like 50 out of 600 satisfy this, or 100 or whatever. So let's see. and we've got 187 out of 600 that actually satisfy the condition of concentrations greater than 0.08. One way to look at the attribute table, because we have it open, is you see some records that are highlighted and some that are not. It might be obvious, these highlighted ones correspond to the ones that are highlighted on the map, and those that are not highlighted correspond to the ones that are not highlighted on the map. There are two different views within the attribute table. Currently we have this view selected, which is show all records, which will show those that are selected and those that are not. Additionally, there is just show selected records, which will show just the turquoise records that we actually have that satisfy this search condition. Now again, with non-spatial queries, let's add a Boolean operator to make it a little bit more complicated. And we want to say parts per million greater than 0.08, and let's say cost greater than 6,000. Two things are going to happen again. This selection on the map is going to change, and within the attribute table, this number of records selected, 187, will change. Go ahead and apply, and we now have 59 records out of 600 selected. And again, I have show just selected records clicked. If we go ahead and click off and show all records, you'll see they're varied depending on whether they were selected or not. Now there's a couple of different things to be cautious of. Let's see, for example, we have just show selected records highlighted right now. If we accidentally add a 0 here, let's say parts per million greater than 0.08 and cost greater than 60,000, let's see what happens. We actually don't have any records that satisfy this condition, because when I created the data, the top value is 6,700 or something like that. There are no records that satisfy the condition of cost greater than 60,000. The other thing is, let me go back to the query we had a second ago. The reason this number dropped was because we have two sections in the query, and the operator we used is AND. Both sections of the query need to be met in order for this to be highlighted here and on the map. We're going to jump to spatial queries in a second, but one thing I want to point out is when you have something selected, two things. Number one, this is a query and it has not created new data. I'll show you how to do that at the end of the video. And the other thing is, let's say you made a mistake and this isn't what you want. Under selection, there is the clear selected features button. It's a little bit hard to find, but just make a note of where it is. Alright, so that is the end of aspatial or non-spatial queries. So for spatial queries, we're asking the computer to show us, based on a spatial location, something that satisfies a condition. For example, what we're going to ask here is, show me all the sample points that are within the grassland shapefile. So again, we can go to selection and select by location. In our select by location interface is a little bit confusing, so just read it slowly. We want the features we're interested in selecting from is the all points file, but in your case it may be something different. This first interface is, what are we selecting for? You could say schools or police stations or something like that. The second one is the source layer. What's the overlapping feature that we want to select with? So in this one, because the question we want to know is the points that intersect grassland, we'll say grassland here. Now, the relationship we want to build is an intersect relationship. There are numerous ones in here. Some of them are more obvious than others, but it'll always default to intersect. So let me go ahead and open the attribute table again to show you what will happen there. Let me say apply. Again, records highlighted, all records, selected records. We have 434 points that are underneath, on top of, however you want to look at it, the grassland shapefile. You can switch it around and say, let's see how many points within the chemical spill area. Those are the points that are within the chemical spill area. There are other bits and pieces you can use to make more complex queries. Let's say we want to say, show me the points that intersect the chemical spill area and are within 100,000 meters of the chemical spill area. Again, 484 and highlighted. We've added those points. Now we have 559 that are points, again, that are within chemical spill and within 100,000 meters of it. That is it for spatial and non-spatial queries. Again, don't forget to always clear selected features. Just want to do a quick addendum to our spatial and non-spatial queries video for exporting data once you have selected it via spatial or non-spatial query. So for all points, let's check our attribute table, and we've got cost again. So we could say select by attributes, cost, again like last video, greater than 6,000, and say apply. This would be a non-spatial query, and we have data selected. If we want to create a new file, you click on all points and scroll to data and export data. And that we'd say samples greater than 6,000. Yes, I do. And those would be, let's say, red is bad, and we'll make them big. These are our really expensive points. The thing here is they're still selected in the old file, which we have here at all points, and we go ahead and close that. And these are our points that are costing us more than $6,000 per spill area. Go ahead and turn that off and turn all points back on. See, they are still selected, and again, we want to clear those with selection and clear selected features. And the same exact process, say select by location, is used for select features from all points. We want to use, say, grassland, all points that intersect grassland. Intersect and apply. Again, just a query, just showing us the data, and we would want to go to the file that we have selected from all points, and we'd say data export. This again is to create a new file if we want it, and we'd say samples in grassland area. Okay, and yes we do. One more time, these are still all selected, so let's go ahead and clear that. Go ahead and turn all points off. And we have our grassland samples. Let's make them giant yellow or purple stars. There we go. That is it for after a spatial query or non-spatial query exporting data to a standalone file. This ends section 1 of spatial analysis and geoprocessing. In section 2, we'll talk about buffering, other proximity functions, and more advanced analysis approaches such as kernel density estimation.